Hi, this is Huda Zenham from Physics 2211 Section M. This is the fourth lab of the semester known as oscillations. The purpose of this lab is to analyze the motion of an object on a spring. In my case, I used a given video and inserted it into the program tracker. Then I used fundamental principles to calculate a computational model using the program growth script, and then compare the results of the model and experimental data, and connect this information to some key ideas. So some key concepts that are involved are the Newton's second law and momentum principle, the energy principle, forces acting on an object, gravitational force and spring force, and then some types of energy that will be contributing to the total energy of the system, which is kinetic energy, gravitational potential energy, and spring potential energy. All of these will be used in the code. Now, for the tracker model, we can see for every second in the time interval indicated, the x and y positions are tracked. And the x and y positions are then, I put it into a spreadsheet so that I can insert it into the code. So we can see here that I have initialized a axes. This is the positive x-axis, the negative x-axis, and the negative y-axis. And I have this calibration stick as a reference point as 0.7 meters. And again, the x and y positions are then tracked over time. So some forces that we have to consider, and with this diagram that was given in the code, we have the gravitational force, which is always pointing downward, our spring force, which is parallel to the spring, and depends, the way that it's facing depends on whether it's compressed or stretched. So if it's compressed, it's pointing down because it wants to stretch, and when it is stretched, it's pointing up because it wants to compress. There's some initial conditions that we have to consider are its mass, which is 0.402 kilograms, which is given, its position, which I established from the first position that is tracked in the tracker model, and a velocity and time of 0. And then we have delta t, which is small enough to create some accurate results. So for our calculations, we have to consider some constant, which is gravitational constant, 9.8 meters per second squared. And we have our spring constant, which I calculated by rearranging our spring formula to get K. And we have L naught, which rearrange again our Hooke's law. And we indicate this by doing the Hooke's law equals to the mg, because in this case, the spring is equivalent to the gravitational force. And then we have calculating L, which is the position of the ball minus the position of the spring, L hat, our unit vector formula, and S as well. So then for these formulas, we have the kinetic energy, half mass times velocity squared, the potential gravitational mass times gravity times height, and the potential spring, half KE squared. And then we add all of these together to get our total energy. So during our while loop, we have to make some calculations that goes through every timestamp and updates our values. So we have our gravitational force, which is negative mass times gravity, our spring force, which is negative the spring constant times S times L hat, the unit vector. And we have F net, which are these two forces combined. And we update the velocity and position using the momentum principle. And again, we use the formulas that we discussed before and to update our values through this while loop. Now here we have 3 charts. This first chart shows change in kinetic, change in potential gravity, change in potential spring, and overall change in energy. All of these are graphed here, and then we have here, we can see that the x position over time and the y position over time. There are some discrepancies in both, mostly in the x, because when we have our tracker model, this data is not completely accurate and specific because we cannot obtain exact results because of the video quality and such. So that's why there are some differences. So what does it mean? We want to see, does this graph satisfy the energy principle? And it does, because delta E equals work is the energy principle. And when we have no work done, that means all the forces are equal to 0. And delta E in this case is the orange line, which is at 0. So this is true. So what does it mean? When we're calculating oscillation time periods in the x and y position, we can see that the data varies, meaning that that's why we have some discrepancies. So to have more accurate results obtained, we could find an average of this period of oscillation to fix some errors. Thank you and have a great day.